Here we're going to talk about how to solve linear systems. Linear systems are just systems of linear equations, so a bunch of linear equations. For example, this set of equations here, we have two equations and two unknowns. So we should be able to solve this system. How do we go about doing that? Well, you could use substitution, you could use elimination. In this case, because the two things are lined up nicely above each other, I think elimination is a good way to go. In order to eliminate, we need to make sure two of the variables match. So we need to basically multiply. So if I want to eliminate the x's here, I need to make sure that the x's are going to cancel out, in which case I would need to multiply this by 3. If I do that, I'm going to end up with 3x minus 2y equals 14. My second equation is going to be multiplied by 3, 3x plus 9y equals 3. If I then subtract these two equations, I'm going to end up with 14 minus 3, which is 11. I'm going to end up with negative 2 minus 9y, which is negative 11y. And of course that 3x's are going to cancel each other out. So I can just solve this equation now. Y is equal to negative 1. Once I know y, I can just plug that into either equation to solve for x. So I'm just going to plug it into the second one because the numbers are a little bit easier to work with. X plus 3 times negative 1 equals 1. Bring that to the other side. X is going to end up being, let me think for a second, 3, 4, right? There we go. So we've solved our system. These are our answers. Now, you might be saying, why? And then, by the way, the answers are in the bottom right corner of the pages as well. I just wanted to check that I got it right. You might be thinking, why are we doing this? This is like a grade 10 exercise. And the reason is because if you look at the next question, we now have to solve 3 equations with 3 unknowns. And how are we going to do that? Can we follow the same process? How are we going to do that? The answer is really yes, we can follow the same process. We can use elimination. We can use substitution even if we wanted to. But what I'm going to show you here is a way to sort of make it more efficient to do this kind of algebra. So I'm going to show you first of all with this question here up at the top, I'm going to show you the way to do that. And we're going to use matrices to do these, or matrices. So the way we do this is, see these two equations, 3x minus 2y equals 14 and x plus 3y equals 1. We're going to write that in a matrix, and we're not going to write the variables down. So I'm just going to write the coefficients of each term. 3, negative 2, and instead of an equal sign, I'm going to put a vertical line there, and then 14. And then the second equation is just 1x, so just 1, 3, and 1. So this is a matrix. It's actually called an augmented matrix because it's not square. And this line here just represents the equal sign essentially. So realize what we have here. The 3 and the 1 represent the x components, right? The negative 2 and the 3 represent the y components, and the 14 and the 1 are just the constant values. So we can sort of do the same process we did with the first by using elimination here, except we don't have to worry about those x's and those y's. So a few things. I'm going to start off by just switching the places of the two equations. And I'm allowed to do that, right? It doesn't matter if I have the first which equation is the first equation and which one's the second equation. You'll see why I do this in a second. Okay, so that's what I want to start with. The reason why I want to start with this is because I want to put a 1 in this top left corner. And an easy way to do that would just be to switch those two equations. Now, what I'm trying to do here is I'm trying to find out what the value of x and y are, right? So remember, this column represents x and this column represents y. So it would be nice if I could make this value into a 0, because what then that's going to happen is going to tell us that this value equals this value. So the y is just going to sort of correspond to that. So all I do to do that is I'm going to do elimination, the same thing. But instead, what I'm going to do, so my first row is okay the way it is. My second row, what I'm going to do is, in order to eliminate that 3 down there in the bottom left corner, I would need to do 3 times my first equation to match up those 3's, and then subtract my second equation. So if we call this equation 1, and we call this equation 2, 1 is going to stay the same down here. But in the second column, what I'm going to do is I'm going to do 3 times equation 1 minus equation 2. There's a minus sign in there. So if I do that, it's like I'm doing 3 times 1 minus 3, which is going to give me 0. Next, I'm going to do 3 times 3, which is 9, minus negative 2. And minus negative 2 is going to be plus 2. So I'm basically going to have 11. 9 plus 2 is 11. And then in my last column is going to be 1 times the 3, which is 3 minus 14 is negative 11. So all I've done here is I've eliminated that x. It's the same thing we did in the left-hand side over here. We eliminated that x by multiplying this equation by 3 and then subtracting. We multiplied that first equation by 3 and then subtracted to eliminate that x. And then let's go back to equations, right? So I remember that this term here represents the y and this term here represents the constant. So I can rewrite the equations now as 11y equals negative 11, and then I can solve that, just y equals negative 1. And then what I can do, I can look at the top equation, right? I can rewrite that out, so this equation here, 1, 3, 1, I can rewrite that out as an equation. So remember the first column is x, so it's going to be x. The second column is going to be y, so plus 3y. The line is equals, and then 1. And I can just plug in my y now, so x plus 3 times negative 1 equals 1. And that gives me x equals 4 when I simplify that. So I got my answers. In this case, you might ask, it actually looks like more work to use the matrices to solve this. Realize it's basically the same math we did in both cases, just one was with a matrix and one was without. So why couldn't we just do this first method? Well, the reason is because basically when we get to bigger and more complicated questions, this actually becomes more efficient because you don't have to keep writing out the x's and the y's, and the process gets a little bit quicker. You'll see that in the next question. So this kind of question is why we use this process instead of doing straight up elimination or substitution. It gets a little bit more complicated when you have 3 equations, 3 unknowns. So first of all, I'm going to start off by writing it out like a matrix. 1, negative 2, and then we have our 2 as our constant. 1, negative 2, 1, and 3. Again, these are just the coefficients of each of the equations. This is a little bit simpler because we don't have to write out the x, the y's, and the z's each time. Remember, this column represents the x's, this represents the y's, this represents the z's, and then those other columns, or that other column is the constants. Now again, the goal of this type of process is to get a matrix that looks something like this. We want to basically have a 1 here with some other number here and some other number here and some other number here. We want to have a 0 here, oops, and then a 1 and then some other number here and some other number here. We want to have a 0 here and a 0 here and a 1 here with some other number here. So we want to try to turn this matrix, our goal here is to try to turn this matrix into something that looks like this. And the reason why is because, think about it, these all represent equations, right? 3 separate equations. If we know that y, remember this represents y, let me actually just write that out again to make it super clear. X, y, z. If we had the equation in this form, this is basically saying z, 1z equals whatever this number is. So that basically finds out what z is. Once we have z, we can plug it into the second equation and solve for what y is. And then once we have y and z, we can plug it into the first equation to solve for what x is. You'll see that in the example that we're going to do here. Just a little bit of terminology. This form of a matrix is called echelon form. Actually, it's called row echelon form because the rows are the things that tell you the answer. Row echelon form. There's also a thing called reduced row echelon form, but we're not going to talk about that. And this process of eliminating the variables like this, it actually has a name as well. It's called Gauss elimination. So it's just another form of elimination using matrices, and it's called Gauss elimination. So let's look at how this actually works. going down to this question. So first of all, remember I want to get a 1 in the top right corner, right? Because that makes it easier to eliminate the x's in the other equations essentially. So the way I can do that, first of all, I can see that there's a 1 in this equation here. Am I allowed to rearrange the equations? Yeah, I can. That's not an issue because you're just putting them in a different order. You're not changing any numbers. So I'm going to just rewrite it, just switching those first two rows. Oops. And then 3, 1, negative 2, and 2, 2, negative 1, negative 3, and 3. Okay, so my first equation is basically good. I don't need to touch that anymore because I have the 1 in the top left corner. The next step is to try to eliminate this 3 down here in the second equation. So the way we can do that, if we think about our elimination, so I'm just going to rewrite out that first line. I can eliminate that if I multiply the first equation by 3, right? If I multiplied this equation by 3, I'd essentially end up with a 3 over a 3, and I can subtract them to get rid of that 3. So that's what I'm going to do. I'm going to do basically 3 times equation 1 minus equation 2. Again, I'll label them. So this is equation 1, this is equation 2, this is equation 3. Okay, so I'm just going to do 3 times 1 minus 2. You don't actually have to show the multiplying by 3. You can just sort of do each of the steps in your calculator by yourself. So 3 times 1 minus 3 is just going to be 0. 3 times negative 2 is negative 6, minus 1 is negative 7. 3 times 1 is 3, minus 2 is 1. 3 times 3 is 9, minus 2 is 7. So there's my second equation rearranged. Now I want to also get a 0 down here in the third row. So I can do that by doing the same thing. Instead of multiplying the first equation by 3 though, in order to eliminate this 2, I need to multiply it by 2. So it's going to be 2 times equation 1 minus equation 3. I'm going to get a 0 down here. I'm going to multiply 2 times equation 1, so negative 4, minus negative 1, which is like saying plus 1. So negative 4 plus 1 is negative 3. Same thing here, so 1 times 2 is 2 minus negative 3, which is like plus 3, which is 5. And then 3 times 2, which is 6, minus 3, which is 3. Okay, so now my second equation is almost good. It actually has a 7 there instead of a 1 in that middle. See, it has a 7 here instead of the 1 in the middle row. So how could we solve that? How could we make that look a little bit nicer? Well, in order to get rid of a 7, you have to basically divide by 7, right? So let me just copy out this first row, which we already said was good. So in order to get rid of that 7, turn it into a 1, I basically need to do row 2 divided by 7. So what's that going to give me? That's going to give me, oh, actually, and it's a negative 7, so I actually need to divide by negative 7 in order to get rid of that. So it's going to be 1, and then negative 1/7, and then negative 1. Okay? Now let's look at our third row. Our third row, we want to get, well, we already have a 0 here, so that 0 is not going to change. We want to eliminate this negative 3 here. And if we look at what we have above it now, we have this 1 above it. So in order to basically eliminate that 1, you know what, actually I'm just going to write out the rest of this line and we'll do it as a separate step. Once you get good, you can sort of do it all as one step, but to make it a little bit simpler for now, we'll do it as separate steps. So let's just copy that out. 1, negative 2, 1, and 3, 0, 1, negative 1/7, and negative 1, 0. Well, actually, let's just leave that for a second. So the third row is the thing we're concerned about. We want to, again, eliminate this negative 3, right? So if we have a 1 above it, right here, again, we can just multiply this row by 3. But because it's a negative 3, if we make it a 3 to eliminate it, we have to add. So we would do 3 times row 2, 3 times row 2, plus row 3 in order to eliminate. right? So this first one's going to be a 0 because it's basically 0 times 3 plus 0, which is 0. And then our second row is going to be 3 times 1, which is 3, plus 3, which is 0 as well. Our next row, we have negative 1/7 times 3, which is going to be negative 3/7 minus 5, or sorry, plus 5 because we're adding this. And when you do that on your calculator, it ends up being 34/7. Keep it as a fraction, it'll save you time later. And then if we do the same thing for the last row, 3 times row 2, so it's negative 3, plus 3 is also 0. So we've made those zeros there in the bottom left corner, which is awesome because now it should be easy to sort of look at what each of these equations represent. Remember, this row, and this row just represent 3 separate equations. So we can always go back to the equations at any point. Notice, by the way, how I also didn't make this this value into a 1, like I said. It doesn't really have to be, because look what happens when we write this out as an equation. So let's look at equation 3. If we write that out as an equation, it's going to be like 34/7, and then the variable there is z equals 0. Well, what value of z makes this true? Obviously, that means z has to equal 0. Right? So we didn't need to actually turn this into a 1 because it's very easy to write out the equation and solve it. So now that we know that z is equal to 0, let's look at our second equation. So we work our way back up, basically. So our second equation, again, coming from down here, our second equation is going to be, if this is x, this is y, this is z, it's going to be y minus 1/7 z, 1/7 z equals -1. That's what equation actually means. We know z is 0, so it's just basically this simplifies as y equals -1. Cool, now we know our z and our y. So let's look at the first equation. The first equation says x minus 2y plus z equals 3. And if we plug in z is 0, that goes away. Y is -1, x minus 2 times -1 equals 3. So we end up with x. So what is that? 2, move it to the other side, it becomes negative, so x equals 1. Let's just check our answers over there. Yeah, look, our answers seem to be right. So our solution to this system of equations is that z equals 0, y equals -1, x equals 1. That is our solution, which matches with the answer on the page. So you can see it was quite a few steps, but doing this with straight up elimination or substitution becomes a little bit more of a nightmare. This is just a little bit easier because you don't have to keep writing the x's and the y's out, and it helps us stay a little bit more organized. So I'm going to challenge you now to try this one yourself. Pause the video here, and when you unpause, I will show you the full solution. But notice how the answer is in the bottom left of the screen, so you should be able to check it yourself to see if it's right. Okay, so this is how I did this question. Your solution might look a little bit different, but this is basically what I did. So first of all, I just wrote out the matrix, and then I rearranged to get that 1 in the top left corner. It just makes it easy to eliminate when we do that. So I just basically brought this third equation up to the top and multiplied it by -1 to make it a positive 1 in that top left corner. Then what I did in the second step is I eliminated that 0 in the second equation by doing 2 times the first equation minus this, made that 0 appear. What it also did is it made a 0 appear here. And then I got -7 and -21. Now think about what this means. If you look at this as an equation now, basically it tells us that -7z equals -21. So our z is 3. It must be 3. So right away we can see what that is. And then what I did, so that's fine. We know our z is 3. So let's go on to that last equation, and let's try to just eliminate that 0 anyways and see what happens. So in order to eliminate, if we look back up here, I needed to multiply this by 3 and subtract it to eliminate. And then I did that for that. And then I got this 2, this -7, this -11. Do I need to go any further? Well, the answer is no, because if I just switch the place of these two equations, it's like we have that reduced form that we talked about. So with the zeros in the bottom left corner. All the values on the diagonal aren't equal to 1, but that's okay, because we can plug in the z equals 3 into this equation to solve for y equals 5. And once we have that y equals 5 in this equation, we could sub in the y and the z into this first equation to solve for x, which is -2. So sometimes, like in this case, you might have other zeros popping up, which actually makes your answer easier to find. A little bit less steps. So you'll notice the next question, accidentally, is just a repeat of the question above it, the question you just did. So let's not worry about that question, we'll just go on to the next page. Okay, here we have another question. Let's give it a shot. So I'm going to go through this one with you because stuff can get a little bit complicated here. Just write out my matrix first. 2, -2, -4, -2, -2, 3, 1, and 7. Okay, there's our matrix. So our first step is to get a 1 in that upper left corner to make everything simple. And we can do that pretty easily by just dividing that first row by 3, right? If we do 1 divided by 3, we should get 1, -1, -2, and -1. So there we have our 1. So now let's look at the second row. We have a 1 up there in the top. So let's sort of ignore this line almost, and let's look at this line here. Right, this line here, we're looking at this, and how we could eliminate that. So essentially what we got to do is we got to multiply this row by 2, and then subtract it in order to get that 2 to become a 0, right? So we're going to go 2 times equation 1 minus equation 2. If this is equation 1, this is equation 2, and this is equation 3. In that case, we're going to get 2 minus 2, which is 0. We're going to get -2, so -4, right? So this becomes times 2, -2, my bad, minus -2, which is plus 2. So that's also going to become 0. Oh, this sort of looks like the previous question. And then -2 times 2 is -4 minus -4, which is 0 again. Sort of interesting. And then lastly, we have -1. -1 times 2, which is -2, plus 2, which ends up being 0. So if you think about what happens here, that first equation completely eliminated that second equation. And why would that happen? Well, if you think about it, it means those two equations are multiples of each other. And if we look back at the question, right, let's look back at these two, or these two. They are multiples of each other, right? If you divided them both by, like if you divided this one by 3 and this one by 2, you'd end up with the same equation. So it makes sense that they eliminated. So that means, first of all, those two things are going to sort of be equal to each other. But let's see what happens when we try to eliminate that third row. So for the third row, I want to get rid of this 2, this -2 down here. So I'm going to take this 1, I'm going to multiply it by 2, and then add it, because if I do that, 2 times 1 plus row 3, because then that's going to get rid of that 2. So I end up with a 0 here. Again, I'm going to go 2 times 1, which would be -2, plus 3, which is going to be 1. I'm going to do -2 times 2, which is -4, plus 1, which is -3. And then lastly, I'm going to do -1 times 2, which is -2, plus 7, which is 5. So if we look at what's going on here, think again about this as x, y, and z. Let's look at that middle equation first, because it's sort of the simplest, right? Essentially, if we think about this equation as just sort of being the z term and the 0, essentially what that equation tells us is that 0z equals 0. Well, does that really help us? It sort of does, because what it tells us is that how many solutions are there to this? There's essentially an infinite number of solutions to that, because I can plug in any value for z, any real number for z, and it's going to give me 0. So there are an infinite number of solutions. So what that tells us is that we sort of have free reign with z here. We can make it any value we want, and it's going to spit out a y value, and it's going to spit out an x value. And when you have that freedom, when you have this sort of situation come up, what you can do is you turn z into a parameter, because it doesn't really matter what that is. So I'm just going to call z t, because it can be anything, and t can be anything. So I'm going to say t is an element of real numbers. And then let's see what happens to our other two equations. So let's go to our next simplest equation, which is our last equation there. We can write it out as y minus 3z equals 5, right? And if we plug in our t there, we're going to get y minus 3t equals 5. Simplifying for y, we're going to get y is 3t plus 5. So this is sort of like a y part of our answer. Over here is our our z part of our answer. How are we going to find our x part of our answer? And the answer is we go to the first equation. So x minus y minus 2z equals -1. That's what our first line in our matrix tells us. And we just plug in what we know. So x minus y is just going to be 3t plus 5. And z is just going to be t. And we can simplify this now. So x minus 3t minus 5 minus 2t equals -1. So simplifying, x minus 5t, and they'll bring the 5 to the other side, adds the 1, so equals 4. So x equals 5t plus 4. So we essentially have an answer, a solution to our system. Now, it's not one solution to our system because t can be any value. But essentially what this tells us is that we have a parametric solution. So a solution, basically we generate a multitude of solutions, an infinite number of solutions by plugging in different t values. And if we look over here at our answer, you'll see that is the same answer that they got. So by making z into a parameter, because we sort of have free reign with it, and plugging into the other equations, we find our solution. So it's not one solution, it's a whole range of solutions defined by those three parametric equations. Let's try the same thing with this one. You can try it yourself, pause if you want, and let's see how far you get. If not, you can follow along with me. I will do it along with you, because let's see what happens. Just writing out the equation. Okay, so there's our system. Our first equation, look, everything is divisible by 3. So I'm just going to divide everything by 3, same as our previous question, right? So I'm just going to show that as 1 divided by 3. And that's going to give us 1, -1, -2, and -1. Oops, that's a negative. So how can we eliminate that 2 in our second row? I could do the first equation times 2, so 2 times 1, and then subtract that second equation from it, and let's see what happens. So I'm going to do, again, let's forget about this row. I like to just cross it out so I don't use it accidentally. I'm going to do this row times 2, so 1 times 2 minus 2, that's going to give me the 0. Then I'm going to do this -1 times 2, which is -2, minus -2, which is also a 0. This might look familiar, a little bit of deja vu. The next one is also going to give us a 0, but let's see what happens with the last one. -1 times 2, which is -2, minus 10 is going to give us -12. Okay, so let's look at what this equation actually means before we continue at all. So remember in the last equation we said that this is x, this is y, this is z, right? So if we rewrite this last equation out with this as the z value, it's going to look sort of like this. 0z equals -12. Does that have a solution? Are there any values for z we can plug in to make that work? And the answer is no. No matter what you plug in for z, you're not going to be able to get 12. So there is no solution. So do we really need to continue with this problem? The answer is yes and no. If we wanted to find a solution for all three of these equations, we know now that there's no solution because there's no value we can use to make that work. So there's no solution to all three equations, but we can then take a step back and look at the equations separately. So we know there's no intersection between the two first equations, but maybe there is between the first equation and the third equation, or the second equation and the third equation. So those we can analyze separately. But for this case, there's essentially no solution for this system of three equations.